Hello and welcome to the course. So before beginning today's lecture, let us first recall what we have studied so far in this course. If you can recall, we started with the data collection process where we learnt about different types of variables and different types of studies. Then we went on to data summarization. Okay, and we saw different summary measures for numerical and categorical variables. After that, we learned different visualization tools depending upon the type of variable. And after that, we learned about an important tool of sampling distribution, which will be useful for our analysis part. So now we are going to cover your data analysis portion, basically from the viewpoint of statistical inference. So today we are going to learn about point estimation, wherein we will learn about two common methods of point estimation, which are method of moments and method of maximum likelihood. So let us begin. Suppose you are interested in assessing the quality of a certain manufacturing process. In this case, the population would be all the items which are manufactured there. And since you cannot obtain data from each and every item, suppose if you are interested in the mean defect rate, you cannot go and check each and every item. Instead of that, you can collect a sample from it, a representative sample out of that population, and then draw conclusions about the mean defect rate based upon that sample. Now, once you have the sample, you can answer this question in three different ways. First thing is that you can compute a point estimate. That means you can come up with a single value that serves as the best estimate for the population parameter. In this case, you will use the sample, and then based upon the sample, you will come up with a estimator for the population parameter, that is the mean defect rate in this case. And as the name itself suggests, it will be a single value, point estimate. Okay. Now, another option for you is that instead of giving a single value, you might think of giving a range of values. Or you can say that you are interested to give an interval within which the population parameter is going to lie with a certain degree of confidence. In such cases, we say that you may choose to construct a confidence interval, which provides an interval estimate for the mean defect rate. So if you can see in the first one, we give point estimate for the population parameter, or you can, that is your mean defect rate. And in the confidence interval thing, you are giving an interval estimate for the mean defect rate. This interval gives you a range of values within which you can be confident that the true mean would lie. So these are the first two options. The other option can be constructed in another way, which is you can test a hypothesis. Now suppose somebody makes a claim about the mean defect rate, and you may think that, okay, if this is the claim, let me test whether the claim that has been made is correct or not. For example, you might want to test the hypothesis that the mean defect rate is below a certain specified level. Okay, so in this case, if it is below and you prove it, then finally you would say that, okay, yes, if it is less than a specified level, it is good because it would reflect upon the quality of the process. Okay, so based upon these three options, you can divide your statistical inference into two major parts, that is your estimation and the other one is your hypothesis testing. And estimation is further divided into point estimation and confidence interval estimation. Similarly, you can consider another example. Suppose you are interested to know the average salary of residents in your city. So in that case, if you want to proceed ahead with this estimation part, you would take a sample and then you would try to estimate, or you would like to come up with a single value that, okay, this is the average salary of people living in your city. Suppose it comes out as 35,000. Okay, so you say that, okay, this is going to be the average salary of the residents of my city. And in confidence interval estimation, you would not pinpoint a single value, but rather you would say that I believe the average salary of the residents of my city is basically between, suppose, 32,000 to 37,000 or 38,000. So here you have provided a range of values. You have given an interval within which the average salary might lie. You are not just giving a single value as you give in the point estimation. Okay. Whereas in hypothesis testing, what one does is that first somebody makes a claim, and your idea is then you want to test whether the claim which has been made is correct or not. Suppose somebody says that the average salary of people living in your city is 40,000, or it is less than 40,000. Now you might think that, okay, let me see if it is correct or not, if the claim which has been made is correct or not. Then in that case, again, you would draw a random sample, which is a representative sample, and then based upon that, finally you will do different analysis and come up with the solution whether the claim which was made was correct or not. So these are the major concepts which come under statistical inference, and now from here on in this course we are going to address each of these one by one. So today we are going to begin with the point estimation. And in point estimation, let us first understand few important terms. So parameter space. Parameter space is usually denoted by this omega, which is basically the range of possible values for the parameter. Okay, whatever your population parameter is, and you would see that, okay, this is the population parameter and what are the possible values that it can take. That basically defines the parameter space. If you can recall, we have studied about population parameter and sample statistic. Okay, so that is why when we say the parameter theta, it means that we are going to talk about the population parameter. Now, since it is a parameter, it would take certain values. In that case, it becomes a parameter space. For instance, if this mu denotes the average CGPA of students in an institute, suppose the CGPA can vary from 0 to 10. In that case, what will be the parameter space? Parameter space would be from 0 to 10, right? Because these are the possible values within which your mu could lie. Likewise, if you are interested to see the proportion of students who miss the quiz, then the parameter space, as we know, proportion would lie between 0 to 1. Okay. So this is the basic definition of a parameter space. So population parameter is the characteristic of the population in which we are interested, and the parameter space is the range of possible values that population parameter would take. Now, recall that a statistic is basically a function of the random sample. That is, if your random sample is x1, x2, xn, then any function that is t of this random sample is referred to as the statistic. Now, when you use this statistic to estimate the population parameter, it now becomes the point estimator, or you refer to it as a point estimator. It is the same thing, but the role now changes. Okay, so you are basically using a statistic to estimate a parameter or a population parameter, and then you refer to that statistic as a point estimator. For instance, you say that sample mean, if you can recall, sample mean is a statistic because it is a function of the random sample, x1, x2, xn. X bar is what? 1 over n summation xi. So this is a statistic. Now, when you use the sample mean in order to estimate the population mean, then it is referred to as a point estimator. Likewise, you have seen sample variance is a statistic, and when you are using it for estimating the population variance, the term is now referred to as a point estimator. And the function t, where you can see that here x1, x2, xn. So these are the realized values of the random variables. So original random variables are xi's, capital Xi's, and their realized values are small xi's. As I have explained this earlier also, the major difference between these. So if xi is representing number of defectives in the sample in the lot, then small x1 would be the particular value, the specific value that you obtain when you check how many defectives are there. Okay, so if the number of defectives in the first lot is 5, then x1 basically, this small x1 becomes 5, or x2 may be here the capital random variable, x2 basically may be the number of defectives in the second lot. Now this x2 over here, suppose you examine the lot and then you finally find that it is actually 2, so this x2 would take the value 2. So likewise, these are the realized values, okay, which is computed from your set of data. Now this function is referred to as a point estimate of theta. So remember that whenever you are talking about capital X bar, that is a point estimator. Okay, now when you fix for this a value, you check the data set, it becomes your point estimate. So that is the major difference between what is an estimator and what is an estimate. Okay, estimates basically refer to the realized values. Once you have found what are the exact values that the random variables are taking, you substitute it, and that basically becomes your estimate. So estimator here, it is basically a function of the random sample or the random variables that you have, and estimate is basically over here a function of these realized values. So remember that whenever you have an estimator, it would be a function of the random variables, that is X bar. So you will use the capital notation for them. And when you are talking about an estimate, it would be the small variables over here, basically, which are the realized values. So this is the major difference between an estimator or an estimate. So now we have talked about what is a point estimator, what is a parameter space, and we know there is a population parameter also is existing, and our interest is to estimate that population parameter. Okay, and we said that point estimator would be basically a single value. We will come up with a single value for the population parameter. In order to do so, we need to know different methods, that how should we proceed ahead, how should we, once we have collected the sample, random sample, then how should we move ahead and finally find an estimator. This means that we need to learn about different methods of finding the point estimators. And for this purpose, we have two main methods. The first one and the oldest one is the method of moments, and the second one is method of maximum likelihood. So we will begin with the method of moments. So before understanding the method, let us first understand the key terms for it. So the first one is, what is a population moment? As you all must have studied in your probability course, that if you have a random variable x and a constant c, then the rth moment of this random variable is nothing but expectation of x raised to the power r. Right? And you know how to find the expectation of a random variable depending upon whether it is a discrete case or a continuous case. So given a distribution, you can find out what are the population moments. And if you have to find the rth moment, so if r is 1, you get expectation of x only, and if it is r is 2, then it is expectation of x square. And the second term over here is the rth moment of x about c. In that case, you have expectation of x minus c raised to the power r. Okay, so c is your constant that we have defined over here. Now, if you see, it is about c. Now, instead of c, I could have mu also here. So it would be the rth moment of x about mu. And in this case, if you see, there is the constant over here is 0. So it is basically x minus 0 raised to the power r. So this is expectation of x r, x raised to the power r, which means that it is the rth moment of x about the origin, about the 0, right? So instead of saying that it is a rth moment around origin, we just say that it is the rth moment of the random variable x. And for this case, we specifically say that it is the moment of x about this point. Now, we often come across the first moment. We know that first moment over here would be expectation of x because r would be 1 in that case. And we denote it by mu. And if you can recall, we have said that mu is basically the population parameter in which we are interested. And the second moment of x about mu, since it is about mu, it will be expectation of x minus mu. So instead of c, you would have mu. And r in this case would be 2 because we are interested in the second moment. And this becomes your variance of the random variable x. Likewise, you can have the sample moments also. So if x1, x2, xn, so they have taken a random sample and you notice that, okay, these are the realized values, that x size, small x size are the realized values, and you have a constant over here. Then the rth sample moment would be 1 over n summation xi raised to the power r. When r is 1, basically you have the first sample moment, which is nothing but 1 over n summation xi, which means it is the sample mean itself. And if it is about a point, then it would be simply, you will subtract that point. So you are basically looking at the distance of each observation from that point and then raising it to the power r and summing up all the observations. That is I1 to n. Thus, the first sample moment would just be the sample mean because r would be 1 in that case. And the second sample moment about the sample mean, that is x, if you substitute x bar in this case, it would be 1 over n summation xi minus x bar whole square. Now, having learned the terms, that is population moments and sample moments, what your method of moment says is that if you have a random sample coming from some population whose PDF or PMF is given to you, and theta 1 to theta r basically means that there are r parameters. So if you know that some basic distributions like your Poisson distribution and your exponential distribution, so these have only single parameter. So in this case, r would be 1. Rather, if you look at normal distribution, gamma, beta, so all these distributions have 2 parameters. So in that case, r would be 2. Okay, so you will have theta 1, theta 2, otherwise you would just have your theta. Now, more method of moment estimators are found by equating the first r sample moments with the corresponding r population moments. So, depending upon the number of parameters, you would be equating the, if there is only one parameter, then you would equate the first sample moment with the corresponding first population moment, and you would solve the resulting system of equations. Otherwise, if there are 2 parameters, then you would need 2 equations. So you need the first 2 sample moments, that is the first and the second sample moment, and you will also need the corresponding 2 population moments also, and then you will solve them. Which basically means that expectation of x, which we saw that this is the first population moment, and here you have 1 over n summation xi, which is the first sample moment. So you would equate these two, and likewise you will keep on going up till the rth one. Okay, expectation of x raised to power r is equal to 1 over n summation xi raised to the power r. Okay, so you would go in this way, you will equate it, and it is very simple to solve these equations. Also, you would see that we are considering here the moments about the origin, okay, because x minus 0, so c over here is 0. In some cases, it might be interesting, or maybe it may be simpler to use the moment about some point, okay, about mean. So in those cases, we can opt for that and compare the population moment about that point with the corresponding sample moment about a point. So in that cases, you will have expectation of x minus, suppose c is there only, so expectation of x minus c raised to power r, you would equate it to 1 over n summation xi minus c raised to the power r, right, where r can be 1 or 2. and so on. So now let us see different examples of finding method of moment estimators. In this case, here we are considering that if you are given a random sample from uniform 0 theta, so we know that uniform over here, right? So theta is the parameter in which we are interested. We would like to estimate this theta by using the method of moments. The second example could be the Poisson one. So Poisson basically is used when we are interested to see how many number of events occur within a given time interval. Okay, so in this case we might be interested in this lambda. So lambda is the parameter that we want to estimate using the sample that we have drawn. And when we go to your 2-parameter case, you have the famous normal distribution with 2 parameters, that is mu and sigma square, and the gamma distribution with parameters alpha and beta. So we will solve each one of them and see what are their point estimators. So we are talking about method of moments, and the first example in this case is your uniform 0 theta. So basically you have a random sample x1, x2, xn which is coming from uniform 0 theta, and you are interested to find an estimator for this theta. Okay, you want to come with the point estimate, that is a single value that would be, you want that particular estimator should be very close to the population parameter, then only it would make sense, right? So let us see how do we obtain that estimator. The method says that, the method of moments we have just studied, that if you have a single parameter, you can equate the first population moment with the corresponding sample moment, right? Since R is 1, that is you have only one parameter, we would be equating the first population moment with the first sample moment. Now what is expectation of x in the case of uniform distribution? Since you know that if a random variable x follows uniform 0, or you can say let us consider a general parameter AB, then in this case, let me rewrite this. AB, then expectation of x would be a plus b by 2, right? So if it is exponent is x is following uniform with parameters 0 and theta, then what will be the expectation in this case? Expectation would be theta by 2. If this is your expectation, right? So we can substitute it over here. So instead of expectation of x, we can write theta by 2. This is equal to 1 over n summation xi is basically your sample mean, right? So now this implies that theta hat is basically twice of your sample mean, right? So this is basically your point estimator in this case. So you have come up with this single value. So you have a random sample, you will find the sample mean and take twice of it. So you will see these examples, that how do they work when we are going to learn about Python in the 4th lecture of this week. Next one was your Poisson distribution. So second is your, suppose Poisson distribution. So you don't have to worry, like somebody says Poisson or Poisson, so it's okay. So let me just use this notation P. Okay. In this case, what will be, here also you have single parameter, so you have to equate expectation of x with 1 over n summation xi. And we know that for Poisson distribution, expectation of x when x follows Poisson with parameter lambda, it is nothing but lambda. Okay, so lambda is x bar, or you can say that lambda hat, that is the moment estimator, is sample mean itself. Okay, now once you know these xi's, okay, so this is the random variables over here. These are the random variables or the random sample that you have taken, or you may consider it as the, so if xi's basically are coming from Poisson distribution, so you know that Poisson is used to see how many number of times a specific event is occurring within the specified time interval or space. So in this case, you might consider x1 is the number of cars, black cars, that cross a particular crossing from 8 a.m. to 9 a.m. right? Similarly, you can go to the second day and note that down, and finally this may be suppose for 10th day, right? Now once you go, so these are the initial random variables that you would be using, and now once you have finally observed that number of red cars that pass, suppose it comes out as 2, second day there are 3 red cars, and finally on the 10th day you have 1 red car. So you have these xi's now. So these are no longer capital xi's, but it is small xi, because these are the realized values, right? Now you have this, so you would refer to this as, you can find the sample mean for this 1 over n summation xi. So x bar over here, this is an estimator. Okay, so this is a point estimator as I defined earlier. Now when you substitute these realized values over here, this small x bar, this would be your point estimate. Okay, because you have now substituted the realized values and then found the sample mean. Next distribution that we had was your normal distribution, normal with parameters mu and sigma square. In this case, as you can see, you have 2 parameters, so you would have to compare 2 population moments and 2 sample moments. So let us consider the first one. So expectation of x would be compared with the sample moment 1 over n summation xi. Expectation of x, we know that it is the mean for normal distribution is just mu, and here it is x bar. So mu hat, that is the method of moment estimator for population parameter or the population mean, is just the sample mean, right? Now if you go to the second one, that is the second moment you compare. So expectation of x square can be compared with 1 over n summation xi square, where I takes value from 1 to n. Okay. So now when you are dealing with expectation of x square, you know that how do we get expectation of x square? See, variance of a random variable is basically expectation of x square minus expectation of x whole square. So if I have to find this value, which basically means that expectation of x square would be variance of x plus expectation of x whole square. So variance of x is what? That is sigma square, and expectation of x, we know that it is mu, so it would be mu square. So this we are going to use over here. So let us substitute that. So here you have sigma square plus mu square. This would be 1 over n summation xi square, where I goes from 1 to n, right? Your interest is in sigma square, right? For mu you have already found an estimate over here. So you can substitute that estimated value now here. So that would become, so sigma square would be 1 over n summation xi square minus mu square. So mu square is basically your sample mean, or you could say that 1 over, you can just write sample mean over here, sample mean square, right? Now you know that if you have this, it is equivalent to saying that 1 over n summation xi minus x bar whole square, where I takes value from 1 to n. How you are getting this from here? If you just open this square, so let me just write it. So I'm just focusing on this part over here. So summation, or maybe I would take the entire thing. So here what you have is 1 over n summation xi minus x bar whole square. Now when you open this, what will happen? 1 over n summation, so this is square, so you will have the first term as xi square plus x bar square minus twice xi x bar, where I goes from 1 to n, right? When you take this summation inside, it would be 1 over n times summation xi square, I takes value from 1 to n, plus this is a fixed quantity over here, so that would become n times of that. So you also have an n in the denominator, so this is n x bar square over n, okay, minus 2x bar over n summation xi, I goes from 1 to n. So here n and n would cancel out in this thing, and here what is summation xi? Summation xi by n again is x bar, okay. So this is 1 over n summation xi square 1 over I from 1 to n plus x bar square that you are getting from the second term minus twice x bar square now, because one x bar is coming from summation xi by n also, right? So when you solve this, what you get is 1 over n summation xi square minus x bar square, where I goes from 1 to n, okay. And this is what we wanted to prove. So we started with this side and we said that this can be replaced with this, right? So now once you have this 1 over n summation xi, this thing, you can recall that if you have, what was your sample variance? Sample variance was 1 over n minus 1 times summation xi minus x bar whole square, where I goes from 1 to n, right? This is what we have defined in your previous week's lecture. So it would be n minus 1 times s square would be summation xi minus x bar whole square, I goes from 1 to n. So here we have summation xi minus x bar square, so we can replace it with n minus 1 times s square that we have obtained here, so which basically shows that it would be n minus 1 time over n s square. So this is basically your sigma square hat over here. This is the estimate, okay. So one that you have found over here is x bar and the other one, so if you have, so estimator for mu and sigma square, if you want to see, it would be x bar and n minus 1 over n s square, okay. So these are the method of moment estimators for your mu and sigma square in case of normal distribution. Next we have the gamma distribution. So x1, x2, xn is coming from gamma with parameters alpha and beta, right? So suppose we consider the form of the gamma distribution as this one, with shape and scale 1 over gamma x to the power alpha minus 1 e to the power minus x over beta, okay. So in this case, if you want to recall, then expectation of x came out as, so x greater than 0 over here and 0 otherwise, so expectation of x came out as alpha beta, and variance of this is your alpha beta square, okay. So this we already know, so let us try to utilize this information, and this case first we will tackle with your first moment. So what we do is that we equate the first population moment with the first sample moment, that is 1 over n summation xi, I from 1 to n. So expectation of x is alpha beta, and here you have x bar. So this is the first thing that you have obtained. But note that it cannot be solved since you have two parameters over here. So we need to find the other one and then it can be substituted. Now, instead of dealing with the second population moment, that is expectation of x square and 1 over n summation xi square, one could also consider the moment about the origin or your moment about your mean. So expectation of xi minus mu square can also be equated with 1 over n summation I from 1 to n xi minus x bar whole square. So this is your population moment about the mean. So here that is why you have population mean, and in this case this is the second moment, right? Second moment, that is why r is 2 in this case, and this is the corresponding second sample moment about the sample mean. Okay. In this case, what is expectation of xi minus mu whole square? This is basically your variance of x, right? Because variance of x, what is the formula for variance? Variance of a random variable is nothing but expectation of x minus expectation of x whole square. So this is the power over here. So in this case also, this is variance of x and this is 1 over n summation I from 1 to n xi minus x bar whole square. Now what is variance of x? Variance of x, we have initially said that it is alpha times beta square. So we can substitute that. So you have alpha times beta square over 1 over n summation xi minus x bar whole square. Now alpha beta here, alpha beta is x bar, right? And what is this? This can be written as alpha beta into beta is equal to 1 over n summation xi minus x bar whole square. So alpha beta is x bar, so beta would be, so x bar can come to the right hand side, so this would be n x bar summation xi minus x bar whole square. Also, you could further simplify this, since summation xi minus x bar whole square, this is n minus 1 times the sample variance and this is n times the sample mean. So this would mean, so beta hat is basically this quantity. Okay, now since you have obtained beta hat, now you can substitute it in the first one, that was alpha beta is equal to sample mean. So if I have to find alpha hat, it would be x bar by beta hat, the estimator that we have found for the second parameter. So if you substitute that, what will you get? So x bar, so it would be n x bar square over n minus 1 times the sample variance. So alpha hat is this. Finally, this is the answer. So the first, so alpha hat and beta hat are these. Okay. So you have seen that how do you compare your population moment with the sample moments, and for this it is important to thoroughly know what are your distributions and what are their PDFs and their corresponding moments, right? If you do not know what is expectation of x or variance of x, then you could not move ahead in these problems. So first of all, brush up your knowledge about the probability distributions, and then it will become very easy for you to compare the population moment and the corresponding sample moments. So in this case, we have seen 4 different examples where in the first 2 cases we had a single parameter and the other 2 distributions which had 2 parameters, and we also saw that it is not necessary that you should always be considering the moment about their origin. Rather, you may consider the second one, that is a simpler in some situations, which is the moment about a point, or you can say that moment about the sample mean or the population mean, as we have done in this gamma distribution case that we have over here.